Hello, this is Tim Tomlanovich. Welcome to Structural Analysis 2 again. We are on our next learning plan. We are now going to compute the maximum shear forces and bending moments of beams. Okay, so, all right. Okay, so let's review, before we start this, let's review beam reaction support. So if you remember from last semester, Um, let me get to the right. So remember, this is a roller support here. So we have a reaction. So this could be a wall here, the reaction there, and then this is a pin support. Okay, so we have a reaction there, and so we have this force here. So I'm guessing we need a reaction going this way to keep that beam from sliding to the left. So we have the reaction X there, reaction Y there, Y there. This would be A, this would be B, okay? And remember, we would want to convert our forces into X and Y for P2Y, P2X. So remember, we're going to, because if these are known forces, we'll solve our three equations of equilibrium. Sum of the forces in the X equals 0, sum of the forces in the Y equals 0. And sum of the moments equals 0 to solve that. So remember, these loads, this could be a wall or something sitting on a floor beam, and then these reactions, the pin roller and the roller and the pin, those are walls underneath there. So these are all external loads acting on the beam. Okay. So again, for this guy, we have a roller here. So we have the reaction in the Y direction there. This is a pin, so that we have a reaction in Y. Okay. We have a load here on the end. This is a cantilever. And remember, this is a uniform distributed load. This will be our line load, pounds per foot, times length. That'll turn that into a point load. And then we solve our three equations of equilibrium. So basically, to solve our reaction loads. Okay. So we will be doing examples with that. All right. So just a review. Okay. So shear diagram convention. A sign convention is necessary for shear moments if the results obtained from their use are to be interpreted conveniently and reliable. Okay. So if I look at this load, so now what we're doing now we're taking all our exterior loads, weights of materials. These external loads are now we're looking on the inside of our beam, because when those loads come onto our structural members, they are bending and they want to shear. So, okay, so we need to figure out what those shear and bending moments are so we can, in the next learning plan, we can actually size these. So we got to figure out that maximum shear and bending, internal shear and bending. So we're taking those external loads and we're looking inside the beam, like we're cutting a cross section in a beam, you're standing inside of it. So if I look here, I have a positive shear when basically the left is staying put and the right is going down. We have a negative shear when you look basically when the left goes up, or I'm sorry, uh, let me back up there. So it's this oops, this concept is kind of hard to figure out. Is it a positive shear or a negative shear? So is the beam, so this one is going up, this one's going down. Okay, this one's going down, and this one is going up. So depending which side of the beam is going in a positive Y or in which side of the beam is going in a negative Y. So it's literally, it doesn't matter if it's a negative or a positive shear. It's just the direction it's shearing. Is it shearing up or is it shearing down? So when we get further in this lesson plan, when you get a negative value, it doesn't mean it's a smaller value. It just mean it's indicating the direction it's shearing internally. So don't worry about it too much. Okay. So these, okay. So if I look here, these are all positive shear, because the right side is going down, and then when you go look at the next lower one, the left side is going down. So there's negative shear. Again, don't worry too much about that. All right, so now moments. I want you to take a look at this. So when we put a load on here, as you can see, this thing it wants to bend. So the bottom fibers end up in tension and the top fibers end up in compression. Okay, now, and if you look here, over here, it's bending down, so we get the opposite effect. Okay, so when you look at a moment, if it's making a smiley face, or if the beam is bending and making a smiley face, we call that a positive internal moment. And if it's shedding water, we call it a negative internal moment. Okay, so when you look here we have a negative moment, and they call this an inflection point. It turns into a positive moment, and then back into a negative moment right at the reaction points. Okay, so again, so there we have reactions here. We're going to solve for reactions first. We're going to calculate the shear as we move along the beam. Okay, we're going to calculate the shear as we move along the beam. And then we're going to calculate the moment as we move along the beam. And basically what it's happening is, because of the deflection and the way it's shearing, it determines if we have a positive or a negative shear. So don't worry about that. We're looking for the largest magnitude, and that's what we design for. Okay. So we always want to work from left to right. Okay, like you're reading a book, work from left to right. So you can work from right to left, but your answers will be the opposite. Okay, so always work left to right. So how do we calculate shear forces? One, solve the reaction forces for the beam. You know how to do that. Solve the reactions using the three equations of equilibrium. Cut the beam at the desired location. Draw the free body diagram of the left side of the beam. FBD stands for free body diagram. And then you sum the forces in the y direction. The sum of the forces in the y direction equals V, which stands for shear. Okay, so now this is not equaling 0. So we make it sum of the forces equals 0 when we're doing equilibrium to solve them. Now there is actually that thickness of member is actually holding up those shear forces, so it's not going to equal 0 anymore. Okay, so that's how you calculate shear forces. How do you calculate bending moments? Again, you solve the reaction forces for a beam. Okay, you don't have to do it twice, because if you solve for shear, you're going to solve for moments. Cut the beam at the desired location, draw the free body diagram of the left side of the beam, and compute the bending moment from a force using the distance from a force to cut point as moment arm distance. Mx equals mb. Okay, so when solving for reaction, solve the whole beam before it is cut, and use the original sign convention for moment calculation. Counterclockwise is positive. Remember that? Okay. Before we even cut it, we need to solve it for equilibrium. Counterclockwise moment is positive. When the beam is cut, and you are, grammatical error there, solving for shear forces and bending moment, any force sense that is pointing up, force sense, remember that's the arrowhead, if that's pointing up is positive, and if it's negative, if it's pointing down, throw away the original moment sign convention, and we'll talk about it. So if it's up, because remember, now our positive shear, negative shear positive moment, negative moment, is the way it's deflecting, the way it's shearing and moving based on the way it's deflecting, okay? So you just, anything pointing up is positive, anything pointing down is negative. When I cut, after I cut the beam, before I cut the beam, I have to use my original sign convention. All right, ready for an example? Okay, so shear force and bending moment, example 1. So what I'm going to do is go into my whiteboard, and then we'll solve this. Okay, so I'm going to go on my whiteboard. So I have all these here. All right, so step 1, solve for reactions. Okay, so here I have a pin. So we're going to have a reaction at point A in the y direction. Here we have a roller, whoops, and we have a horizontal one. But remember, that's going to be 0. You need to show it even though it's 0. The reaction at point A in the x direction. And then we have the reaction at point B in the y direction. So this is example 1. Okay. All right. So now solve reactions. Okay. So so you draw your free body diagram. Remember that. Sum of the forces in the x direction has to equal 0, comma. There is no horizontal forces, so Rex equals 0. Sum of the forces in the y direction has to equal 0. So we have the reaction at point A in the y direction. It's positive because I'm looking at my sense. Minus 10 kips at point C plus the reaction at point B in the y direction has to equal 0. And we can rearrange that equation. The reaction at point A in the y direction plus the reaction at point B in the y direction has to equal 10 kips. So now we're going to use the third equation. Sum of the moments about point A. Remember, you want a subscript there so I know which point you're rotating around, equals 0. Okay, so we're going around A. So we got the 10 kips here. Remember, we didn't cut the beam yet, so we're using original sign convention. So that 10 kips is going clockwise around point A, so that's a negative moment. Minus 10 kip. My perpendicular distance from the line of action to the point of rotation times 6 feet. Okay. RB, the reaction at point B in the y direction, that is going counterclockwise, so that's positive. Reaction at point B in the y direction, and my perpendicular distance is 10 feet, equals 0. Okay, so now I want to solve. Let's solve that. I'm just going to slide up here. So we have 10 RBY equals 60 kip feet. The reaction at point B equals 60 over 10, which equals 6 kips. So this equals 6 kips. So now I do substitution. So the reaction at point A plus the reaction at point B, which is 6 kips, has to equal 10 kips. So the reaction at point A has to equal 4 kips. Okay, and we know this equals 0. So now make sure you check equilibrium. Don't forget this step. Check equilibrium. Okay, so all this is one step because it's review. Okay, sum of the forces in x equals 0. Reaction at point A in the x direction has to equal 0. That's true. Sum of the forces in y has to equal 0. So we have 4 kips minus 10 kips plus 6 kips equals 0, and that is true. So this is where you're going to catch your mistakes. So remember, you want to rotate around a different point. So I did A when I solved. Now I want to go around point B. Again, I have not cut the beam yet, so I'm using original sign convention. All right, so the reaction at point A is going clockwise around point B, so that's a negative rotation. And that is 4 kips. Okay. Times 10 feet. And then we have this 10 kips here that is going counterclockwise. So that's a positive, plus 10 kips, positive rotation, times 4 feet. And that has to equal 0, and it does. Okay, so now our reactions are solved. Okay, so that was step 1. Now let's move into step 2. And let's see if I can actually move this down so we can see what's going on, which is really cool. All right. So we know this equals 6 kips, this equals 4 kips, and this equals 0. Okay. Now I want to solve for the shear in the moment. Okay. So basically, sometimes what I need to do is I want to find the shear in the moment at a specific location in my beam. For an example, we may want to find it right at 6 feet to the right. So if I just, let me erase so we can see the dimensions there. Okay. Or sometimes, as plumbers and HVAC people do, is they'll cut holes in your joists or your beams, and then you want to figure out the shear and moment at those points, so determine if we're not going to break the beam. So that's why in pre-engineered joists they have pre-knockouts. That's important for that planning, so those get designed. So what we're going to do is we're actually going to cut the beam, okay, and we're going to go from the left side right at 6 feet. Okay. So, step 1, free body diagram. Whoa. Of the cut. Okay, let me erase this. Okay, we did step 1. Solve the reactions before cutting. Okay. So this is, okay, I'm going to call this step 2. All right. FBD of cut. Okay, so if we look here, let's draw our beam. So we show everything that's there. We have 6 kips there, and then we have 10 kips there. Okay, and then we know the dimension from here to there is 6 feet. Okay, so our cut point, remember, is right here, and this will be our imaginary rotation point, is right there. Okay, now step 3, find my shear at 6 feet, because that's where I'm cutting it, is 6 feet from the left, equals the sum of the forces in the y direction, and that equals, so remember, now we're in our new sign convention, because I'm looking at my new free body diagram in step 2 there. Anything pointing up is positive, anything pointing down is negative. So equals 6 kips minus 10 kips, that equals minus 4 kips. That equals my shear force, or my shear load at 6 feet. Okay? So it's a negative shear. I don't care if it's negative or positive, it's just the way it's deforming. I'm just looking at that magnitude. Okay? Now, let's find the moment at 6 feet, which equals sum of the moments. And remember, I am using this as my rotation point, the cut point. Okay, so I go left to right. Okay, so 6 kips. Okay, so it's pointing up, so it's positive. I don't care about rotation anymore. If it's pointing up, my load vector, my sense is pointing up, it's positive. 6 kips times 6 feet, right? Because I'm 6 feet to my rotation point. Okay, I'm looking, I keep going across from left to right, minus 10 kips times 0, because the line of action is right through the rotation point. So that equals 6 times 6 is 36 kip feet is my moment at 6 feet. Okay, so basically, now if I move this cut, say a foot past 6 feet, say it's at 7 feet, so now I would actually, my shear would stay the same, but my moment would change, right? Because then I'd have 10 kips, negative 10 kips times 1 foot. And this, my moment at 7 feet would be 26 kip feet from the left. So basically, cut your beam where you want to determine where it is. Draw the free diagram to the left. Only show what you can see at that cut, and then you calculate from there. Okay, let's do another example. And that one, okay. So again, let's just repeat. Solve the reactions before I cut the beam. Check equilibrium. Cut the beam where you want it. Calculate the shear, calculate the moment. Okay, so you can do all at once. Okay, so let's do another example here. Let's look at this guy. So this is example 2 in your PowerPoint. Okay. All right, so we have A, we have B. So let's make our line load. Oops. Let's make that 100 pounds per foot. And let's make our beam length L equals 10 feet. Okay. So again, we have a step 1, solve the reactions. Reaction at point A in the y direction. Reaction at point B in the y direction. Reaction at point B in the x direction. We know that's going to be 0. Okay. All right. So step 1 is solve reactions. Okay. All right. So step 2, remember, we got to get everything in x and y. Well, not step 2. Remember the process, make sure everything's in x and y, and then convert any distributed loads into point loads. So if I look here, I have a distributed load. This is a rectangle, so it's 5 feet from the middle. So my moment arm distance is 5 feet. So is 100 pounds per foot times 10 feet times my length, and that equals 1,000 pounds. Okay? All right. Step. Oops. Again, I'm just making this all step 1. All right. Sum of the forces in X direction have to equal 0. Reaction at point B in X direction equals 0. There is none. Okay. Sum of the forces in Y has to equal 0. So we have the reaction at point A in the Y direction minus 1,000 pounds. That's the distributed load turned into a point load, plus the reaction at point B equals 0. So the reaction at point A plus the reaction at point B in the Y direction has to equal 1,000 pounds when I rearrange that with algebra. Okay, sum of the moments. Point A has to equal 0. All right, so we go 1,000 pound number. I have not cut the beam, so I'm using the original sign convention. So we have 1,000 pounds. That is going clockwise. So that's a negative rotation. Times my moment arm distance to point A is 5 feet. Okay, and then the reaction at point B in the Y direction is going counterclockwise, so that's a positive rotation. And that's your magnitude of your sense times 10 feet. And this all has to equal 0. So, okay. So now the reaction at point B in the Y direction has to equal, that's 5,000 divided by 10 is 500 pounds. Okay. So now we do substitution. The reaction at point A in the Y direction plus 500 pounds has to equal 1,000 pounds. The reaction at point A equals 500 pounds. So when you look at this, remember me showing you the trick WL over 2, and you get the same answer. I just want to review moments. Right? Half of that 100, see, 100 pounds per foot times half of it's going here, half of it's going there, times 5 is 500 pounds. Okay, check equilibrium. So I'm going to call this was step A, step B, C, D, E. F is check equilibrium. Okay. Sum of the forces in the X has to equal 0. The reaction at point B in the X direction equals 0. Sum of the forces in Y has to equal 0. So we have 500 minus 1,000 plus 500 equals 0. Check. Sum of the moments about point. Now we're going to use a different point equals 0. Okay, so RAY is going in the clockwise rotation. So that's a negative. minus 500 pounds times 10 feet. Okay, and then the point load of 1,000 pounds is going counterclockwise around point B, so that's a positive, plus positive rotation, pounds, and that distance is 5 feet, and that does equal 0. So we're good. All right. So I'm going to slide this down. So we can do our okay. So we know, let's see, let's clean this up a little bit. Okay. We know this is 0, so we don't need to show that. So this equals 500 pounds. The reaction at point B in the y direction equals 500 pounds. Okay. And we know this is 100 pounds per foot. Now, when I cut my beam, I do not want to convert it into a point load. We got to leave it the same as the original load. So I'm taking that off. Okay, so I want to determine, we know that's 10 feet. Let's say I want to determine, okay, I want to know my shear and moment at 5 feet in. Okay, 5 feet from point A. All right, so now step 1 or step 2 of the whole process, okay, is free body diagram of cut. Okay, so let's draw that out. So here's our beam. Okay. Whoops. I don't want this side. How do I get rid of that? We have a distributed load of 100 pounds per linear foot. Okay. I have my reaction at point A in the y direction. That equals 500 pounds. And then right there, that equals 5 feet. So when I cut it at 5 feet, that's the only thing I'm seeing. Okay. So now, 3. Again, do not, you gotta remove that conversion of the distributed load to the point load back to the distributed load, because you actually see a distributed load on this 5-foot cut. So if, say I wanted to cut it before 5 feet, you would not see that point load, but there is a load there. So basically I'm shortening up that line load. Okay. So now if we want to solve the shear at 5 feet, and that equals the sum of the forces in the y direction, and that equals, so if it's positive, now I cut the beam, now anything pointing up is positive, anything pointing down is negative. So 500 pounds, okay, minus 100 pounds times, right, pounds per foot, times the length of my cut beam is 5 feet. So if I do that up, my shear at 5 feet is actually 0 pounds. So I have 0 shear, and yes, that is okay. Equals shear at 5 feet. There is a point where, basically I'll tell you this now, where maximum moment is where the shear equals 0 in a beam. So basically when I keep adding my shear, so if I do it at 1 foot, cut my beam at 1 foot, so I'd go 500 pounds minus 100 times 1, so that my shear is 400 pounds. My shear at 2 feet is 500 pounds minus 2 times 100, so it's 300 pounds. So the shear is actually going down, and then it's turning negative as I go past that midpoint. So if I go the shear at, let's just say at 7 feet, so I add 500 pounds minus 100 times 7, so that's 700. So I have a negative 200 pounds of shear force. So it's switching the direction the way it shears inside, internally. Okay? So now my moment at 5 feet, M for moment, V for shear, equals sum of the moments from left to right. All right, so 500 pounds is pointing up, so it's positive. Times 5 feet. Okay. Now I actually got to convert that into a point load. I'm going to do that all in there because it's a 5 foot length distributed load. I got to do it the same as I would before I cut my beam, except this is why this is important, because your shear will be inaccurate. So now this is pointing down, so minus 100 pounds per foot, that's my line load, times 5 feet, right? That turns it into a point load. That step turns it into a, okay? That turns it into a point load. Now I know that that goes, basically, if I just do a hidden line here, it goes in the middle. So from my rotation point, which is here, it's 2.5 feet away. Okay. Times, this is my moment arm distance, times 2.5 feet. Okay. So that is moment arm distance. Okay. So when I calculate that out, so I take 100 times 5 times 2.5, that's 1250. So, okay, so 500 times 5, oops, I didn't do the whole thing. So 500 times 5, that's from the reaction load, equals 2500, and then I need to subtract 100 times 5 times 2.5, and I get 1250 foot-pounds. 1250 foot-pounds. That is my moment at 5 feet over. Okay. All right. So different examples. So remember in this slide, so step 1, solve reactions. Before I even cut it, check equilibrium. Step 2, find out where you want to cut it. Okay. Draw your free body diagram of your cut section. Remember, you got to remove that point load. Okay. Then solve. And then you solve for the shear in a moment. And remember that distributed load turns from the tire beam length just to the left side, and we have to reconvert it into a point load. But do not do that. Do not do that when you calculate the shear. Only when you figure out the moment arm distance in the shortcut section. Okay, that 2.5 feet. That's when you turn in, only in the moment equation is when you turn it into a moment arm or point load. Okay. All right. So that's how you calculate shear and moments about any point. So you could have something you want to hang from your joist or your ceiling rafters, and I need to know what that shear moment is at that point and see what that extra load is, okay? But now to size the beams, all right, is like we need to find the maximum shear and the maximum moment, positive or negative. I'm looking for that magnitude, but I don't want to have to cut that beam every foot to figure where that is. So I'm going to do a shear and moment diagram. Okay, and that is our next. So I'm going to go back to the PowerPoint. So that was example 1. We did example 2, and we'll be coming right back to these. Okay, so when I look at the shear and load diagrams, if I look here, this is my load diagram. That's basically your free body diagram. I have my reaction solved. Okay, here's a distributed line load, and here's a point load. So basically what you can do is I draw lines down and I just basically calculate the shear. So if I look here, my point load comes down, because remember, any sense pointing down is negative, anything pointing up is positive. So I go down a magnitude, and as I look, it stays constant because there's no load between here and here. And then all of a sudden I hit this reaction load, AY, and that you take this load and I add this. So this plus this will give me this, right? And now for every foot, it's dropping on that distributed load. So it keeps coming down until I get to point B, and then I add this load, this reaction, and it should equal 0. Okay. Key is 0. It always goes back to 0. So now, and I look at the moment, right? If I don't know how this curve goes, is basically I could cut this beam every foot and calculate the moment and the shear, and you can create little data points and make your curve. So I look here, I have a negative moment, okay, and then because I have a negative moment, because I have a negative shear, and now I have a positive moment because it's a positive slope, because I have positive right here. I have a positive, I'm on the positive side of the 0 point. So right here, as you see, 0 shear equals maximum moment. And then here I have a negative shear because I'm below the 0 line, so my slope is going down. And I'll explain this in more detail. Okay, so these are actually fairly easy. All right, so let's go. Let's talk about the load curve. So when I have when it's a rectangle, it's called a 0-degree curve. So we're talking about calculus terms here, but don't freak out. All right, 0-degree curve means it's a rectangle. Okay, so when I go from my distributed load, which is a 0-degree curve, if I look here, from here to here, 0-degree curve, I go to a 1-degree curve, which is a triangle. See, that looks like a triangle. And then from a 1-degree curve, I have to go to a 2-degree curve, which is this. Okay, it's a curve. So 0, 1, 2. It always has to increase in curve numbers as I go from load to shear to moment. So you always do your shear first, then your moment. So if I look at a point load is not a 0-degree curve. It's nothing. So if I go from a point load down to my shear, now I go from a 1-degree, and now I go to a 2-degree. Or I'm sorry, nothing to a 0-degree to a 1-degree. Okay, so this was 1-degree, 2-degree, as you can look. So let me write this out. So this is nothing. Point loads are nothing. So this is a 0-degree, and this is a 1-degree. So this line load here is a 0-degree, this is a 1-degree, this is a 2-degree. So 1-degree is a triangle, right? It's straight. Okay. All right. So 0, 1, 2. So rectangle, 0 degree, triangle, 1 degree, parabola, 2 degree. Okay. And so shear diagram construction, solve reaction forces for the beam. So you're doing that same step. Before I even cut it or anything or start drawing, I need to solve those reaction forces. Sketch the load diagram to scale. Remember, the load diagram is your free body diagram. Draw the horizontal baseline representing zero shear. It should be directly below the load diagram in the same length. Project lines vertically downward from key points, each reaction and concentrated load, the beginning and end of each distributed load, and then sketch shear diagram using continuous summation of the shear forces starting at left side of the beam. Locate points of zero shear. Okay. So I'm just going from left to right. Moment diagram. Create the shear diagram first. Draw a horizontal baseline below the shear diagram, the same length. Project these lines down, reaction and concentrated load, beginning and end of distributed load, and points of zero shear. Then sketch the moment diagram using summation of areas from shear diagrams starting on the left side of the beam. Okay. Shear diagram. Force senses pointing up are positive and pointing down are negative. Moment diagram. When the shear diagram area is positive, above the zero line, above the zero shear line, the slope of the moment diagram will be positive up and to the right. When the shear diagram area is negative, below the zero shear line, the moment diagram slope will be negative down and to the right. Okay, if you keep those points in mind, this should be fairly easy. All right, back to our example. So I'm going back to that same example. All right, so I'm going to go back to my whiteboard. And, okay. All right, so all right, so here we go. So step one was find the reactions, A and B, right? So I solved those already. And those are over here somewhere. RAY is 4 kips, RBY is 6 kips. So you'll have to do this again, right? I don't need to do it because I already solved it. Check equilibrium. Okay, so we're going to write this. Oops. Ah, can't rest my hand on there. So this is 4 kips. And then reaction at point B in the y direction equals 6 kips. Okay, so I'm going to slide this over. I'm going to get the ruler out here. So the first thing you do is you draw a zero line. And then this is why engineering paper works great. Typically I like to use the horizontal. I do, 1-to-1 and in the vertical. So I make each box like 10 kips, 5 kips, so you don't have to match the vertical and the horizontal scales. So that's what I typically do. So let's draw our zero line. Same length of the beam here. So we go to there, all the way to there. Because if I look, this transfers down, right? That's the length of my beam. Okay. So this is 0, this is plus, this is negative, and this is shear. And my units are in kips. So make sure you write your units down. All right, so now what I want to do is project lines down. So beginning and the end of each reaction, which I have, right? So basically what you want to do there, okay, the beginning and end of any distributed loads or point loads, okay. Okay, it's not quite 90 degrees, and right, because these points don't change. Okay, all right. Okay, so let's pull the ruler off. All right, shear. RAY is 4 kips. So I'm going to make 2, 4. I'm going to make each, so this way, each way is 1. Okay, so this is, so I didn't quite make it to, so I'm going to just draw it there. All right, so this is 0. This is the positive side, this is the negative side. This is shear again. This is kips. All right, so RAY, boy, that's a horrible Y. That's a Y there, by the way, equals 4 kips. Okay, so 2, 4. Okay, draw my line. Okay, now if I go all the way, it stays constant until I hit that point load right there, because nothing changed. You don't see any other loads in there. Okay, and then from 4 kips, I got to subtract 10 kips. So 4 minus 10, because this is the sense is pointing down, so I get -6. So that's 2, 4, 6. So the distance from here to here is 10 kips, right? But I'm going from +4 minus 10, so I end up at -6. So the length of this line is 10 kips. Okay. Then nothing else changes. See, it's constant. And then I hit my reaction and I go up 6 kips. Okay. So this is a positive area. This is a negative area. And then we know this distance is 6 feet. We know this distance is 4 feet. Okay. All right. So the key is at the end of your shear, it should go back to 0 in a simply supported beam. Okay. Now, if I have a reaction somewhere in the middle and I have that overhang, it still will go to 0, and be careful where your reactions are. Okay. So that is my shear diagram. So this, see, this is a point load. So this is a 0-degree curve, and this is a 0-degree curve. Okay. So now if I look, I have points of 0 shear right there. Okay. So that is my shear diagram. So if I look here, my maximum shear, so, and then what I recommend too, what I'd like to see, this is -6, and then this is 4. This points where it changes, okay, where it changes magnitude. So I am going to design this beam for 6 kips of shear. It's a negative shear, that means it's breaking the other way, but this is the largest magnitude. So there, I just found my maximum shear force. Okay, now let's do the moment diagram. So moment diagram, okay, I just keep projecting my lines down. Right below, so points of 0 shear, beginning and end of line distributed loads, where your reactions are. Okay, just project that down. Okay, and now I need to draw a moment curve. So we'll do that right here. And we're going to make that our 0 moment. And okay, so this is, oops, moment, and this is kip feet. So this is the plus side. This is the negative side. And this is moment, kip feet, kip times feet, plus side, negative side. And this is 0 moment, 0 moment. Okay, so we're going to call this area 1, call this area 2. So what I'm going to do is actually calculate the area. The area of the shear curve is equal to the magnitude of the moment. So if I go area, okay, so I'm going to take 4 kips, right? That's the height of my rectangle is 4 kips because I went to 4. And I multiply it times my length, which is 6 feet. I get 24 kip feet. Okay? And that's a positive. Now I look at this area, I get minus 6 kips times 4 feet. I get a negative 24 kip feet. Sorry. So this is positive 24 kip feet. This is a negative 24 kip feet. Now when I add, because from the left side all the way to the end of that beam, no matter what, it should equal 0. So if I add this, this should equal 0. Okay? And it does. Now, the moment diagram. So this is a 0-degree curve because it's a rectangle. So now I go down to a 1 degree, so that's a triangle. So my moment right here is 0. But my moment at the end of this shape here is 24 kip feet. So I'm going to make this 10, 20, 5, 10, 15, 20, 25. So right about there. Okay. Now I need to draw a straight line. Now, if I look, because this is a positive shear, it's above my 0 line, I know my slope has to be positive. So it's up and to the right, and it's a 1-degree curve. So that means it has to be rectangular. It has to be a triangle. Okay. All right. So this is 24 kip feet. Okay. So now, remember, it's a summation from there to there. So I have 24 kip feet. Then I got to add this negative moment here, and I get 0. So I go back down to 0 because it's a summation from left to right. Left to right. So basically, so now from this point, I know it starts at 24 kip feet and it drops down to 0 because I'm taking 24 kip feet plus this area 2, which is a negative area, and that's why it goes down to 0. So this is a 0 degree, so this also has to be a 1 degree. So, and then I go like this, and there we go. That is 1 degree, and this is a 1 degree because it's a triangle. So now, my maximum moment I'm going to design for this bending moment is 24 kip feet, which is right there. So that is a shear moment diagram. Okay, so if I don't know what the shape is, I can cut this beam every foot and create my data points and draw it. But just knowing that the area underneath the shear curve equals the magnitude of the moment, I can use the area method, and as long as it has to go back to 0. So that is the shear and moment diagram. Again, how do I start? I got to solve these reactions using the original sign convention, and then anything pointing, once I get in here, anything pointing down, anything pointing up, and is negative. Okay, so let's do the next one. So I'm just going to slide this over. All right, so here we go. This is this problem. We know, again, we want to use the original free body diagram. This equals 100 pounds per foot. Okay. So we know this is 500 pounds because we solved it before. Remember, you solved the reactions. All right. So that is the load diagram. Load diagram. Okay. So next thing is I project my points down from the beginning and the end of the beam. So I'm going to just give myself plenty of room here. So that's the first reaction. Second reaction. So, and that's also the beginning and the end of my distributed load. It's right at the reactions. Okay. So now I can draw my shear point zero shear. Okay. And we'll make that blue. Draw a 0. Okay. So we know this is 0. This is positive shear. This is negative shear. And this is shear is V. I don't know why they call it V, and our units are pounds. Okay. So let's go up. So from 0, I start here at the 500 from left to right. I go up 500 pounds. 1, 2, 3, 4, 5. Okay. All right. Now the question is, so 100 pounds per foot. So every foot, my shear is going to drop 100 pounds as I go from point A all the way to point B. So 100 pounds times, remember my length is 10 feet. So from this point here of my 500 pounds all the way down to here minus 1,000, right? 500, I'm adding plus a negative 1,000 because these are pointing down. I get a negative 500. 1, 2, 3, 4, 5. Now, this is a 0-degree curve. Okay. So now, what I do is I have to draw a 1-degree curve. Okay. All right. So this is negative 500, right? And then once I get to here, then my reaction at point B is 500, so I go back to 0. Okay. So I just created 2 triangles. So this is area 1. This is area 2. Now, if we look here, we have a point of 0 shear. It crosses 0. So how do we find that? Okay, we know that actual answer. Oh, why does that keep doing that? Must be pushing the note button here. So remember, I need to transfer a point of 0 shear down. Okay. All right. So how do I find point of 0 shear? So I'm going to slide this over. Number the original 0 shear. Okay. So if I know it's somewhere around 5 feet. I mean, obviously it has to be 5 feet, but let's say it's not at 5 feet. So I'm just gonna cut it at some distance X. Okay. And then make X here and X is there. Okay. X is that distance. That's what I'm looking for. I'm looking for this distance X right here. This is X. Okay. So if I cut the beam at some distance X and figuring out what distance X, the value of shear equals 0, I set up an equation and solve it. So if I go from left to right, so if I go 500 pounds Okay, and then my distributed load is minus 100 pounds per foot times some distance x, and that equation has to equal 0 because this is actually 0 right there. So now I solve for x. So x equals what? Okay, so you go 500 pounds. This moves to the positive side, so 500 divided by 100, x equals 5 feet. Okay, so this is a symmetrical beam, but you may only have a partial distributed load, so it's important you can find that. So, and then this is 5 feet, because we need to know the length of our triangle. Okay, all right, so that's how you do that. So now let's do our moment equation. So I'll just start it up here. Hopefully I have enough room here. Beginning and the end, I projected down my point of 0 shear. So this is moment, this is 0, this is a positive moment, this is a negative moment, and this is pound-feet for my units. 0 moment plus minus pound-feet or foot-pounds, however you want to say it. Okay, area 1. So this is a positive area, this is a negative area. Now that I know my length of my triangles by finding a point of 0 shear, so oops, area, so area 1, and that is 1/2 times, because we have 500 pounds, times 500 times 5, right? Pounds, feet, foot pounds. 500 times 5 times half of that, so I get 1,250. So I can slide this over a little bit. 1,250 foot-pounds. Okay. So area 2, I get 1/2. So now I have a negative 500, right? Because I have a negative, my height is a negative 500. It's a negative shear because I'm on the bottom side of my shear curve times 5, and I get a negative 1,250 foot-pounds. Okay, now, so I could have several areas across the shear curve. I want to make sure that equals 0. Okay, so we know this is a 1 degree. This is a 1 degree because why? Our load diagram, we had a 0 degree, so we went to a 1 degree. So now we got to go from a 1 degree to 2 degree, which is a curve, parabola. All right, so the moment is 0. If I take a look at this free body diagram, 500 times 0 is 0, right? There's no moment arm distance. There's nothing there. Okay, so we know at the end of this shape, okay, I have a moment of 1,250 foot-pounds. So 500, 1,000, 1,250, or so yeah, 2, 4, 6, 8, 10, 12. We'll just make it, let's see, 500, 1,000, 1,250 right there. So I put my moment diagram too close to my shear diagram. So this is 1,250. Okay. And then when I add 1,200, this is a negative shear, so I go back to 0. Okay. Positive. So from here to here is a positive shear, so I have a positive slope. I have a 1 degree curve. 1 degree curve on the shear, so I have a 2 degree, so it's an arc. So I got to go up, and then this is a negative shear, so that means I have a negative slope, so I have to go back down. So it's a sketch, so I know this is 2 degree, this is 2 degree. There is my moment curve. Okay, so I'm going to design this thing for 1,250 foot-pounds of moment and 500 pounds of shear. It's a positive moment, so that means it's smiling, right? It's smiling. The deflection of this thing is like this. Positive moment. See? It makes sense that that beam is wanting to deflect that way. Okay, so we have a positive shear until we get to here, then it switches the direction. Now remember, we're looking at the grains of the wood and the steel, what's happening inside. Okay, so that's that guy. All right, I'm gonna take a little 5-minute break here. So okay, hello, I'm back here. So let's go to our last example problem here, and then you can get right to your homework there. So let's go here. I'm just gonna slide this over more. Let's take a look at this problem. All right, step one, I'm gonna solve the reactions and everything above here, so we can draw our lines right below it. Okay, so step one, solve reactions using original sign convention. Okay, so we need to create our free body diagram. So I'm going to use red so they stick out. So the reaction at point A in the y direction, we have the reaction at point E in the y direction. Okay, I do not have any horizontal loads, so we know that there's no horizontal force reaction, so I can eliminate that. Okay, so with that, we can go sum of the forces in the y direction has to equal 0. So we have reaction at point A in the y direction minus 5 kips minus 10 kips minus 8 kips plus the reaction at point E in the y direction has to equal 0. So if I reduce this equation, the reaction at point A in the y direction plus the reaction at point E in the y direction has to equal, so 10 plus 5 is 15 plus 8 is 23, and that turns positive when I move it over to the other side of the equation. Okay, sum of the moments about point A has to equal 0. All right, so the 5, the 10, and the 8 kips are all going clockwise around point A, so those are negative moments. So we have minus 5 kips, and that's a negative rotation times 4 feet. Negative 10 kips, negative rotation times 6 plus 4 is 10 feet. And then 8 kips, that's going counterclockwise around point A, so that's a negative rotation, so that's why I'm saying minus 8 kips times 15 feet. And then reaction at point E in the y direction is going counterclockwise, so it's a positive rotation, that's why I'm writing plus. And reaction at point E in the y direction times 10, so that's 20 feet all the way to point A. And that has to equal 0. So doing algebra and math, I'll do this. So we got 5 times 4 plus 10 times 10 plus 8 times 15 equals, divided by 20, I get 12 kips. Okay. I substitute. So RAY plus 12 kips equals 23 kips. RAY equals 23 minus 12 equals 11 kips. That's going to do this 5 times 4 plus 10 times 10 plus 8. Yep. Okay. That equals 11 kips. All right, substitution. So this was 1A, 1B, 1C is substitution. So remember, before you start A, we make sure everything's in X and Y, and all point loads, or all uniform distributed loads, are converted into point loads. Okay, so D, we got to check equilibrium. Okay. Sum of the forces in Y has to equal 0, so we go 11 minus 5 minus 10 minus 8 plus 12 has to equal 0. 11 minus 5 plus 10 plus 8 minus 12 equals 0. Let's see, 11 minus 5 minus 10 minus 8 equals 12 plus 12. Yep, that equals 0. Okay. And we are going to sum in a moment about point E has to equal 0. Do a different point. So the reaction in point A in Y direction is going clockwise around E, so that's a negative rotation, minus 11 times 20. Now all these point loads are all going counterclockwise, so those are all positive rotations, plus 5 times, let's see, we got 6 plus 5 is 11, plus 5 is 16, plus 10 times 10 plus 8 times 5 equals 0. Let's see if that's true. All right, so 8 times 5 plus 10 times 10 plus 5 times 16 equals minus 11 times 20. All right, I did something wrong there. 11, let's see, 5, 11. Okay. 5 times 16 plus 10 times 10 plus 8 times 5. So that's 220. There we go. So when I add these three positives, 220, 11 times 20 is 220, so that does equal 0. So we're good. See, this one is not as easy to determine if I did my reactions right. So I'm good. All right. Now, solve reactions. That was step 1. Step 2. Okay, let's draw out our, so I'm just going to erase this so this doesn't interfere with our diagram. Okay. So let's get the ruler out and let's which project our lines down. So the beginning and end of each beam, okay? There's that. I'm just going to give myself a little more room here. Then we'll go back and forth so we can see each point load, right? This is why engineering paper works wonders. Okay. All right. Okay, now I can draw. I'm going to move this down so we can see. Draw my shear 0 point. Make it right there. Okay. This is my 0 mark. This is positive shear. This is negative shear. This is V stands for shear, and my units are kips. Okay. You should always label your axes using your units. You don't have to do both sides. Okay. All right. So first we go up 11 kips. So 5, 10. I'm going to make each of these 5. So I go up 11 kips. Okay. It does not change until I hit this. Now it goes down 11 minus 5. We go down to 6 kips. Okay. And then it stays constant. Okay, so this is 6 kips right there. Okay, now we're at 6 kips minus 10. We got to go down 4 kips. Okay. All right. So 6 kips minus 10 is -2. -2 kips. So I got to go below. Now we just crossed the 0 line. Because remember, this line right here is 10 kips long. This line here is 5 kips long. I'm just subtracting, right? It's a summation. 11 kips minus 5 is 6 kips. Minus 10 is a -4 kips. Okay. And so if we do that, so this is 4. Okay. And then up here, we go a negative down another 8, so we get the 12, which is right there. So this is 12. Stays the same because I'm right here, stays the same. And then it pops up back to 12, or to 0, because I'm adding 12. Okay? So remember, it should go back to 0. So now let's take a look at our areas. Okay. So basically this is what you want to do. That's an area. That's an area. That's an area. That's an area. Okay. So we're going to call this area 1, area 2, area 3, area 4. Even though this does not intersect that, we can still make those areas. So we have 4 different areas. We have 2 positive and 2 negative areas. Okay. Do I need to project any further points down? Any points of 0 shear? We have it. It's already at that point load, so we don't need to add a different line. Okay. So now let's calculate our areas. So we don't need to calculate the point of 0 shear. Okay. And remember, these are 0-degree curves now, each of these, and I would like you to identify those as point of 0 degrees because they are rectangles. Okay. So area 1. All right, so we go to 11 kips, and we multiply that by our length is 4 feet. So that equals 44 kip feet. Area 2 is, all right, so no, you just want the height of the rectangle, not, okay? So this is 11 kips high. Now what's this height? Okay, so see that? That's 6 kips because we went 11, so this rectangle is 6 kips high. 6 kips from 0 to this point right there. That's 6 kips times 6 feet equals 36 kip feet. Okay, area 3 is now -4. So remember, there's a negative there, right? Because we just want the height of the rectangle. Minus 4 kips, that's my height of my rectangle, times 5 feet equals minus 20 kip feet. Okay, and then area 4 is minus 12 kips. It's the height of my rectangle times 5 feet, and that equals a negative 60 kip feet. Now, when I add these together, they should be 0. 44 plus 36 minus 20 minus 60. They equal 0, so that's a good sign. All right, so now we have our areas. Okay, so now all of these are 0-degree curves, so now we're going to have 1-degree curves, right, triangles. Okay, so let's get the ruler up here, and let's create our 0x, or 0 point for our moment curve. All right, so let's go there. So this is 0 moment. This is the plus side. This is the negative side. This is moment, and this units are kip feet. That way you don't have to keep writing units in there. All right, so now it starts at 0, has to end at 0. Okay, so if I want to go find the moment at that first line that I project down is at 44 kip feet. So 10, 20, 30, 40. Okay, 20, 40, 44. Right there, I'm going to draw a point. So that's 44. Okay. Now 44. Now I want to find the total moment at the end of area 2. So that's from 0 to there. I just add 44 plus 36, which is 80. So I got to go 36 more. So, and I'll end up at 80. So let's see here, 10, 20, let's see, what did I do? 20, 20, 40. So each one is 20, 20, 40, 60, 80. Okay. So basically what did I just do? At the end of area 2 is 80 kip feet. Okay. So this is 80. Okay. Now at the end of area 3, I got to subtract 20. I go back down to 60, right? Because it's a summation from left to right. So now if I go here, I'm at 60 kip feet. So I go down 20. And that's right there at this end of area 3. So that's 60. Okay. And then I go another 60 and I end at 0. Does that make sense? Because remember, it's a summation from left to right. So now, knowing that these were 0-degree curves, these have to be, the shear was 0-degree curve, the moments has to be 1-degree curve. Okay, so area 1 is a positive shear shape above the 0 line, so it's a curve, its slope is positive, so it goes up and to the right. Okay, Area 2 is also a positive shear area. It's above the 0 mark, so it's positive up and to the right. Area 3 is a negative shear moment, so it has to be a negative slope. So it has to go down and to the right. So, and actually my data points actually help me determine that. And then area 4 is also a negative shear area, so I go down and to the right. It's a negative slope. So that is what my moment diagram looks like. So this will be a 1 degree, 1 degree, because you can create rectangles on that, okay? Or not rectangles, triangles. It's triangles. It's a linear line is a 1 degree curve, calculus terms, okay? So that is it with the examples, okay? Fairly simple if you just follow the same procedures, use the area method. Okay, so now I want to, so that was that example, and I just did this example, the shear moment diagrams. So here's your homework. So go through your homework, go through the example problems, and then I'll be posting the quiz soon. And please contact me if you have any questions. Thank you.